class we are talking of the spanning scanline algorithm. Sorry, we are talking of the scanline Z buffer algorithm. Okay. Today I will briefly repeat the I'll briefly repeat the scanline Z buffer algorithm, and then we will go into the spanning scanline algorithm. In the scanline Z buffer algorithm, we have seen that if this is our screen, then we will cover the screen row by row. We will first take the first row of pixels, then the next row of pixels, and so on, and then at each row of pixels we will consider all the polygons that are intersecting that row of pixels. Okay. So, if we have a set of polygons like this, then at each row, let us say at this row, we will consider all the polygons that are active, and within each row of pixels we will see at each pixel what is the closest polygon to the eye, and for deciding the closest polygon to the eye at each pixel we are maintaining a Z buffer, and the size of the Z buffer we said would be proportional to the x direction resolution of the screen. Okay, that means for each pixel we will be maintaining the current closest polygon to the eye. So, this way we will first scan convert one polygon, then the next polygon, and so on, and for this we said we need to maintain an active polygon list, and for each polygon we will be maintaining an active edge list. Okay. This active edge list, this terminology is from the earlier algorithm that we had for polygon filling. Okay, that is scan conversion of polygons. In this active edge list, if you remember earlier, we were keeping track of the x intersections for each edge. We are keeping track of the x intersection, we are keeping track of delta x, that is the shift in x intersection as we move from one scan line to the next scan line. Okay, and we are keeping track of delta y, that was the remaining number of scan lines left for that edge. Okay, that means let us say if I am considering this edge and this edge ends over here, then delta y would correspond to the number of scan lines in this portion. Okay, and every time we are going from one scan line to the next scan line, we are decreasing delta y by 1, and the moment delta y became 0, that edge would be deleted from the active edge list. Now, in this case, in addition to delta x and delta y, we will also maintain a z and a delta z. Okay, this z value would be the depth of this edge, okay, the z value for this edge at this intersection point. Okay, and this delta z will be the change in this depth value as we move in the x direction. Okay, that means if we have a polygon like this, and this is the scan line we are considering, this is the value of z at this intersection. As I go into the next pixel, the depth of this pixel is going to change, but since we are talking of a planar surface, this change in depth is going to be the same as we move along the x direction. That means delta z in this portion would be the same as delta z in this portion, and so on. Therefore, in the active edge list we will maintain a delta z value which will tell us the change in the depth of each pixel as we move in the x direction. Okay, and this way we will have an active edge list which will give us the z value, that is the depth of each pixel in that polygon. So, when we are scan converting this polygon at this scan line, we can easily compute the z value at each pixel. Okay. So, z of x y can be very easily computed. and if this z of xy is greater than the z buffer at x, okay, in that case this particular pixel will be displayed according to this polygon. Okay, so if this condition is satisfied, then we will have to update z buffer as well as the frame buffer. Okay, and this process of scan converting each polygon will be repeated for all the polygons in the active polygon list. Okay. So this is the scanline z buffer algorithm. It's essentially a modification of a z buffer algorithm, modification to the extent that now we will be maintaining a z buffer for only one line, and as we move from one scan line to the next scan line, we will use the same z buffer for our computations. Okay, the amount of space required in the z buffer will be proportional to the x direction resolution. Okay, so this is an improvement upon the z buffer algorithm to this extent. In the z buffer algorithm, we are using space which is proportional to x multiplied by y. Here we are using space which is proportional only to x. Yeah.
So the delta z which we have,
yeah,
it's the unit movement in z as we go along x or y?
As we go along x.
So how do we account for the unit movement as we go along y?
Okay. Good, you pointed that out. What we'll have to do is we'll have to maintain a delta z in the x direction as well as a delta z in the y direction. Okay, delta z in the y direction will be used as you go from one scan line to the second scan line. Delta z in the x direction will be used as you go along the x direction. Okay, as you go from one pixel to the next pixel in the x direction. Okay, you will have to maintain both delta zx and delta zy. Okay, thanks. Okay, any other questions on this algorithm? Okay, now within the same algorithm, let's see a small situation. Let's say we have one polygon like this, and we have a second polygon which looks, let's say, something like this. Okay, and we are considering a scan line at this location. In this algorithm, what we are doing is we are starting from the first pixel on the screen. When we come to this intersection, this is the first edge we have in the active edge list. From this intersection onwards up to this intersection, we are finding out the value of the z, and then if this is my polygon number 1 and this is my polygon number 2, my z buffer in this region will contain details of polygon 1. Okay, will contain depth according to the polygon number 1. But for computing the depth, we are computing the depth at each of these pixels. Okay, then I'll start with this intersection and compute the depth at this pixel and so on. Okay, so effectively what we are doing is I'm computing the depth at each of these pixels. Okay, but in this region, let's say from here up to this point, computing the depth at each pixel is absolutely redundant. Okay, because in this region we have only one polygon. Okay, so even if I am computing the depth, the same polygon is going to be displayed. Even if I am comparing every time with the z buffer, that's unnecessary because the same polygon is going to be displayed. Similarly, in this region, I need not do all the computations purely because I know that the same polygon is going to be displayed. Okay. In this region, Now I have got 2 polygons. Again, here also I will be doing a lot of wasteful computation, because since we are talking of planar surfaces, this polygon and this polygon can intersect in only one point in this plane. Okay, if I draw this plane like this, okay, mind you, on this screen I am drawing the x and the y planes, and here I am drawing the plane corresponding to this scan line. Okay, that means if you are looking at the screen like this, I am drawing a plane perpendicular to the screen now. Okay, the plane perpendicular to the screen would be the x z plane. Now in this xz plane, the intersection of a horizontal plane, this xz is a horizontal plane, okay, the intersection of a horizontal xz plane with any of the polygons can only give me a straight line. Okay, 2 polygons can only intersect in a straight line. So if I consider this polygon number 1, maybe it will intersect something like this, and polygon number 2, it can intersect either like this, or maybe it can intersect like this, or it can intersect like this. Okay, we will consider all the 3 cases. Okay. In the first region, that is in this region, we have only one polygon. As we can see here also, we will have only one polygon. So we know that only this polygon has to be displayed. In this region, okay, if this is the intersection, that is case number A, this is case B, and this is case C. In case A, this polygon is behind this polygon. Okay, so I am going to display this polygon. Okay, because this polygon drawn in green is in front, polygon number 1 is in front. I am looking at it from this side right now. Okay. In case number B, from this point to this point, polygon number 2 will be displayed, and from this point to this point, polygon number 1 will be displayed. Okay, and in case C, my polygon 2 is going to be displayed because that is closer to the eye. That is in this region. Okay, and then if I consider this region, in all these 3 cases I have only one polygon, and that is polygon number 2. Okay, so here I am going to have polygon 1, here I am going to have polygon 2, and in this region I will have either polygon 1 or polygon 2 or a combination of the 2, depending on what type of line of intersection we have. Okay, but nevertheless there is no need to compute and compare the Z buffer at each of the pixels. Okay, I only need to decide that in this region only one polygon will be displayed, and I will display that polygon. Okay, I need not compute the Z value and compare that with the Z buffer at each of these pixels. That is unnecessary. Okay, so we will again modify the scanline Z buffer algorithm to take care of this. What we will do is we will divide this screen into a number of spans. Okay, where each span, or where spans will be defined to go from one endpoint of a line. I am talking of these intersections. Okay, in these intersections the spans will be defined to go from one endpoint to another endpoint, or to this is an endpoint, this is also an endpoint. Okay, so wherever we have endpoints, our spans will terminate there. Okay, I have an endpoint here, I have an endpoint here, and I have an endpoint here. I also have an endpoint here. Plus, wherever I have intersections, wherever I have any two lines intersecting, I will have another span ending over there. Okay, so in this case, we will have a span ending here, we will have a span ending here, we will have a span ending here, here, and here. Okay, now span is essentially dividing this x axis into a number of regions. Okay, so spans are basically regions in x direction. Okay, and spans they terminate either at endpoints, line endpoints, or at intersections. Okay, so if we have spans terminating at endpoints or at intersections, we can have spans of this kind. If we have two lines, two polygons intersecting the xz plane, at these two lines, my spans would be defined as starting from x equal to 0, going up to this point, then from here going up to here, then here, here, okay, and beyond that. So this is our span number 1, this will be span number 2, this will be span number 3, this would be span number 4, and this would be span number 5. Okay, so this way, and this would be span number 6. Okay, so this way the whole screen or the complete scan line along the x axis will be divided into a number of spans. And the important property would be that in each span only one polygon will be displayed. Okay. There will be no span in which more than one polygons can be displayed. Okay, in span number 1, nothing is being displayed. Okay, actually instead of only one, I should say at most one. Okay, in span number 2, I will have this polygon being displayed. In span number 3, this polygon will be displayed. In span number 4, this one will be displayed. In span 5, this will be displayed, and in span 6, nothing will be displayed. Okay, again I am looking at this is my direction of viewing. Okay, the only thing that remains is how do I decide as to which polygon is to be displayed in a particular span. When I have only one polygon in the span, it is very easy to decide which polygon will be displayed. Okay, but when I have more than one polygon, okay, let's say in this case we have two polygons, I basically got to decide as to which polygon is closer to the eye. Okay, I can either look at the z value at the end of the span, either at the starting end or at the last end. If I look at the z value at the starting end, okay, at the starting point of the span, in span 1 there is no confusion, in span 2 there is no confusion. In span 3 I look at the z value here and the z value here, and I will decide that this is the polygon to be displayed. But in span 4 there will be a confusion, because the z value at the starting point would be the same for this polygon as well as for this polygon. Okay. Similarly, if I look at the end point, there will be confusion in span number 3, because at the end point the two polygons will have the same z value. Okay, so to avoid this confusion, what we will do is we will compute the z value of all the polygons at the midpoint of the span. Okay, that means we will look at the midpoint of span number 2, midpoint of span number 3, midpoint of span number 4 and midpoint of span number 5. If I am looking at the midpoint of the spans, I can easily decide which polygon will be visible and which will not be visible. Okay, if I am looking at span 3, at the midpoint I can easily decide this is the polygon to be displayed. In span 4 also, if I look at the midpoint, I can decide that this is the span to be displayed. Okay, so to decide which polygon is closer to the eye in a particular span, we look at the midpoints of the spans and compute the z value of the polygons at the midpoint. Okay, so this is polygon 1, let us say polygon A, and this is polygon B. I will compute the z value in span 3 for polygon A at the midpoint, at this point. Similarly, for polygon B, I will compute the z value at this midpoint, and we will find that ZB is less than ZA. Okay, therefore we will display ZB.
Is there any necessity of computing at the midpoint?
See, the only thing is if you compute at any of the two endpoints, there is a possibility of confusion. Okay, but then you will have to also look at the other endpoint and then decide. Okay, so just to avoid confusion, maybe you can look at the midpoint. Okay, let's say you are looking at the starting point. If you are looking at the starting point, think of span number 4. In span number 4, the z value for polygon A will be the same as the z value for the polygon B at the starting point. Okay, because that is a point of intersection. Okay, therefore what we will get here will be ZA will be equal to ZB. So how do you decide which is closer? You cannot. If you are looking at the end point, then the same confusion will be there for span 3. Okay, just to cut down this confusion, you can uniformly decide that you look at the midpoint. Okay. Any other point on this algorithm? Okay, in this algorithm, if you notice, we are not using any Z buffer. Okay, no Z buffer will be used. Okay, because we have divided the width of the screen into spans, and at each span we are deciding which is the closest polygon. Okay, so we don't need the Z buffer, plus we are not scan converting every pixel of every polygon. Okay, so speed will also be better for this algorithm. In the previous algorithm, we are taking each of the polygons, scan converting each and every pixel, okay, for all the polygons, and then deciding which is closer to the eye and which is further off. Okay, in this case, we are not doing that, so speed of the algorithm will be better, and we are not using the Z buffer, so the memory requirement will also be lower. Yeah? How do we get the intersection point? We know the equation of this line, we know the equation of this line, we can find out the intersection. Okay. Essentially, if you have a number of polygons, we will have a number of lines like this. We will have to find out all possible intersections. Okay, and then divide the screen into spans like this.
Couldn't we have done the same thing using a Z buffer by seeing at the active polygon list at each pixel along?
At each pixel?
Yeah, and seeing the active polygon list, there are 3 polygons active, and comparing their Z values, whichever one is the lowest.
But then you are doing it at each pixel.
Yeah, that's a scan line method.
Yeah, so then you'll, at each pixel you'll compute the Z value for all the polygons.
Yeah.
Right? That's going to be slow. In this case you are not doing that. In this case, let's say you have one polygon here, another polygon behind it, another polygon, we have a set of polygons like this. In span number 5, you will compare the Z value at the midpoints of all these polygons and decide that this is the polygon which is the closest. Okay, and then you will compute the Z value for only these pixels, only these points. You won't compute the Z values for each of these polygons. For these polygons, you will compute the Z value only once.
For that part where we have to do once we go through a polygon and again we are scanning through the same another polygon, we have to update the Z buffer only at the intersection points where it's overlapping. So that means essentially that whenever the active polygon has contained more than one polygon.
But you'll be dividing that into spans anyway.
Yeah.
If you're dividing that into spans, then you don't need the Z buffer at all. Okay, what you're saying is to compare the Z value at the midpoints. You will maintain a Z buffer. You don't need that. You only need to maintain one variable as to which is the closest polygon. Okay, you don't need to maintain a complete Z buffer just because you want to decide which polygon is close at one particular pixel.
Right.
Okay. Any other point in this?
So
Okay.
doesn't the computational complexity increase very highly as the number of polygons increases?
That will happen in every algorithm. Even in your scanline Z buffer, as the number of polygons increase, you will have to scan convert each and every polygon.
So that's of order n. This is of a higher order.
Why?
So
that's
calculating the number of intersection points.
Calculating the number of intersection points. Okay, that can be speeded up considerably by again dividing the whole thing into span and deciding which are the which polygons are active in a particular span. We'll compute intersection only for them. Okay, finding the intersections can be done much more efficiently.
So we can compute the intersection lines between the polygons and those lines go to
Intersection lines.
yes, sir.
Oh, what you're saying is this intersection point
Form the line.
that will form a line. That can be done. You can maintain that intersection line, and as you move from one scan plane to a second scan plane, you can change that accordingly. That can also be done. Okay, intersections can be computed much more easily than doing a complete scan conversion. Okay, that is why it is better to do more intersections than to spend all the time in doing the scan conversion. Any other question on this? Okay. In that case, I'll just write down this algorithm in a formal manner so that if there is any confusion we can take care of that. The first step will be for each polygon will determine the highest scan line intersected by it. Okay, and then we'll place the polygon in the Y bucket of that scan line. Okay, sure. Remember we have done a similar thing when you are doing polygon filling. Okay, there we have taken every edge and placed that in a Y bucket. Here we will take every polygon and place that in the y bucket, so that we'll know when a polygon is starting, and then we can compute when a polygon is going to end. Okay. Then for each scan line now, okay, let's say if I call this an array y bucket yb, okay, for each scan line we'll examine the y bucket for any new polygons. Okay. We'll add new polygons to the active polygon list. Okay. Then we'll say update active edge list. Okay, we'll have to update the active edge list and then divide into spans. Okay, once I have updated the active edge list, I can easily find out the set of lines in my xz plane. Each of these lines like this can be obtained from the active edge list. This point is going to be on the active edge list, this point is also going to be on the active edge list. Similarly, this point will be on the active edge list and this point will also be on the active edge list. Okay, so from the active edge list, I can divide my region into spans, and once I have divided the region into spans, okay, then in each span you decide the closest polygon or decide which is the closest polygon. Okay, and then we'll say increment y and go on to the next scan line and again update active edge list and the active polygon list. Okay, some edges would have come to an end, we'll have to delete those edges. Some polygons would have come to an end, we'll have to delete those polygons. Okay. So this would be a sequence of steps involved in this. Okay. Now if you notice between this algorithm and the previous algorithm, that is the scan line Z buffer, the portion that is actually different is this portion. Okay, in the previous algorithm, instead of dividing it into spans, we were scan converting every polygon. Okay, the rest of it was more or less the same. Even there we had to maintain an active edge list and an active polygon list. Okay, only this portion was different in that algorithm. Okay, here we are dividing it into spans and thereby saving on time.
We need to compare the like we have to the intersection of those lines. Only then we decide.
Yes.
But those intersectional lines, that means that we are comparing Z values. We have the equation of those lines.
Yeah, but the intersections we found mathematically, not by comparing the Z value at each point.
Doesn't that mean the use of the Z buffer?
is your x direction, this is your z direction. Okay, I have a line here and I have a line here. I know the equation of this line, I know the equation of this line. I can find out the intersection. Yeah, I know how to find you know how to find intersection between two lines. Okay, I don't have to compare the z value here, 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 and keep comparing and then decide. That is not the way I'll find the intersection. Intersection will be found just by mathematically writing down the equation of the line and solving it. Okay. Any other question on this? What is the active edge? The active edge list. The active edge list see, this is my xz plane. My active edge list will tell me that for every polygon, okay, if I am looking at it from front, that is in the xy plane. Okay, if you remember this figure, this edge is active, this edge is active on this scan line. Similarly, this edge is active and this edge is active. Okay, so the active edge list will give me the intersection of this edge, the intersection of this edge, intersection of this edge, and the intersection of this edge. With the xz plane. So if I am looking at the xz plane now, the active edge list will give me a point here and a point here, plus a point here and a point here. Okay, in the xz plane, the active edge list will only give me points. Okay, once I know these points, I know the equation of the line between them. Okay, if I have a let's say if I have a polygon like this and a scan line like this. Okay, now this I am talking in the xy plane. My active edge list will contain this edge, this edge, this edge, and this edge. If I look at the same thing in the xz plane, okay, maybe I'll get lines like this. 1, 2, 3, 4. This point is point 1, this point is 2, this is 3, and this is 4. Okay. Okay. So the active edge list will give me these endpoints. From that I'll get the equation of this line and then use that to divide it into spans. Okay. Any other question on this? Okay, in that case we'll go on to another algorithm, and that is called the floating horizon algorithm. Now, this floating horizon algorithm will be used for displaying surfaces. Okay, if I have a surface, something like this, okay, where the surface can be given mathematically by equation of the type f of x, y, z is equal to 0. Okay, if my surface is given by given in this form, in that case I can use this floating horizon algorithm. Essentially what we will do is we will take vertical planes, okay, parallel to the xy plane. I will take one vertical plane like this, then I will take another vertical plane which will be just behind it, and then another one just behind that. Okay, so we will take a set of vertical planes and compute the intersection of these planes with the surface that we have. Okay, so if I take the intersection with the z equal to constant plane, I'll get a curve. Okay, this is one surface and I have a vertical plane. The intersection of this surface with this plane is going to give me a curve. Okay, that curve will be of the form, let's say f of xy or f prime of xy will be 0. Okay, this way we will get a set of successive curves, one behind another. Let's say with the first plane, if I get a curve like this, with the plane just behind it, I get another curve which looks something like this. With the plane behind it, I get another curve which looks something like this. I'll keep displaying each of these curves. Okay, but if I get a curve which looks something like this in the next plane, then I'll display only this portion of the curve. Okay, so the next curve, if that looks something like this, okay, again if I look at the next curve, it might look like this, and so on.
So, how come you don't start from the back planes then?
If I start with the back planes, then I'll have lots of problems. Look at this. If I start from the back plane, okay, let's say I've drawn this curve. Now I'm taking a plane which is ahead of it, so some part of it is going to be obscured. Okay, let's say the next curve looks something like this, and this curve in red is in a plane closer to the eye. So this portion of the curve is not going to be displayed now. I'll have to delete that. Okay, so a portion of figure which has already been drawn, I'll have to go and rub this out. I don't want to do that. I'm first looking at the plane which is closest to the eye. Once I've drawn that, I know for sure that that is not going to be rubbed ever. So all the other planes are behind that. Okay, that is why I first consider the plane which is closest to the eye, that is this plane. Then I'll consider a plane which is just behind it, and then I'll consider the next plane which will be behind it like this. Okay, so one by one we'll consider all the planes. Okay, and we'll keep drawing these curves, and along the length of the curve we'll keep track of the fact that portions of the curve might be behind portions that have already been displayed. Okay, and when would this portion be behind a curve which has already been displayed? That would be when the y value for this curve, mind you, this is in the xy plane now. Okay, when the y value for this curve becomes less than the y value for a curve which has already been displayed. Okay, this curve, this one, has already been displayed. Now I am trying to display this curve. At this point, the y value for this curve, this is let's say curve number 2 or curve number b, and this is curve number a. The moment the y value for the b curve becomes less than the y value for the a curve, that means this b curve is hidden. Okay, so we will make use of that fact, and then we will display each of these curves one by one, keeping track of the y values.
You have to store the y values of all the curves.
Yes, not all the curves, the current highest,
Maximum.
the maximum y value at the current location.
Suppose it's like a wave.
Even
Different curves will have different maximum y values, so we store the maximum
No,
y values of
at
y.
each x pixel, we will have to store the maximum y value at that point.
Of any curve.
Whatever the curve be, the maximum y value at that point. We'll see this algorithm in more detail in the next class. Okay, because the details will take some time. We'll see the details in the next class.
How do you decide the increment of the planes?
That is by a decision which has to be taken on the basis of the nature of the curve. That could be random. Okay. So that's all for today. We will complete this algorithm in the next class.